is at atmospheric pressure, meaning that above the water table you have unsaturated soil with atmospheric pressure in it. The confined aquifer is upper limited by a rocky layer, or anyway an impermeable layer, which means that the aquifer is under pressure. It's the pressure of the aquifer at the upper limit is higher than the atmospheric pressure, and therefore if you make a well here, you go into the confined aquifer, it may happen that the groundwater rises up and rises out of the well without pumping. Instead, if you pump from the confined aquifer, usually you need to pump water, and the effect is a lowering of the groundwater table. In both cases, you see that even for the confined aquifer, if you take water, you may decrease its pressure, and therefore saltwater intrusion may come into it in both cases. Usually the risk is lower for the confined aquifer, because if the pressure in the aquifer is high, then the risk is lower. But still, even for confined aquifers, groundwater exploitation may be an effective driver. So let's focus on the dynamics of saltwater intrusion. This is an handmade drawing made by me, because I couldn't include in the page a figure that I found particularly nice. And let me just try, I understand that this figure, especially if projected, is not very clear, so let me explain a little bit better what it means. What happens here? So, we have a groundwater aquifer which is fed up by infiltration. It's unconfined, and below it we have a confined aquifer. Okay, let's focus on the unconfined aquifer. It's fed up by, it's replenished by infiltration, and also it may be replenished by a river. If in some cases, we already talked about it, in some cases we have rivers draining the aquifer, in some cases we may have rivers feeding the aquifer. In the water in the aquifer is fresh water, it's used by plants, and therefore plants take some water. And also we may have some wells here, and if we take water from the aquifer, of course, so we lower its level. And if the replenishment is sufficient to compensate the withdrawal, nothing happens. If the replenishment is not sufficient, then we have saltwater intruding. Saltwater comes from the sea, and at the coastline we have that the seawater penetrates into the soil. Of course, this happens if there is permeability. So if you have a rocky coast, usually you are not concerned by saltwater intrusion. Also in rocky coasts, usually you don't have a lot of groundwater resources. So typically you are not much concerned, neither by saltwater intrusion, neither by the fact that groundwater may be contaminated. You are concerned when the coast is permeable, because it is permeable. The fact that it is permeable means that probably there is a groundwater aquifer into it. In a permeable soil, you have usually aquifers. And the fact that it is permeable means that you can have infiltration through the seabed, infiltration of salt water. If you have a lot of flow into the aquifer, you don't have to be concerned. You have a flow from the aquifer to the sea, which is fine, and prevents saltwater intrusion. In order to make sure that there is this flow, we already discussed about this, the level of the water table must be higher than the sea level. So usually when the soil is permeable, but you have the level of the water table that is higher than the sea level, this is fine. You have a flow from the land to the sea. But keep in mind that fresh water is lighter than salt water. Salt water is heavier than fresh water. So the level of the water table must be quite higher than the sea level. If they are at the same level, you have saltwater intrusion, because salt water is heavier. Is this clear? To give you a number, you know what is the weight of fresh water is 1,000 kilograms per cubic meter. An average value of weight for seawater is 1,024 kilograms. It's not a big difference, but still it makes a difference. So, let's go back to what happens. You have saltwater intrusion, and the saltwater intrusion takes the form of a salt wedge. Do you understand what is wedge? In Italian is cuneo, and in English it's spelled W-E-E-G-E. It takes the form of a wedge. Why? We will see why. Next slide. And I want to anticipate why. Because as you move inland, typically the groundwater level gets higher, and therefore more pressure of fresh water. It means that the level of salt water goes down, because the level of groundwater raises up. This is the reason why we typically have saltwater intrusion in the form of a wedge. And so we talk about saline wedge or cuneo salino in Italian. Our technical problem is to estimate the shape of this wedge, so the position of this interface. In this figure you see also another reason of concern, urbanization. Urbanization, and which also means water demand. Okay. Yeah.
Can you explain again why we have a wedge?
Okay, the premise is that the next slide will provide a mathematical explanation. Now let me provide a conceptual explanation. I think it is also important to give a conceptual explanation. Okay, of course the mathematical explanation also gives you the conceptual explanation, because this is a general rule that you should apply. When you look at, I think I already told you this, when you look at a mathematical relationship, you don't have to focus just on the mathematics. You have to focus on the implications, the physical implications in terms of processes that you are dealing with. But of course, sometimes it's not easy. So this is why I would like to make to anticipate the conceptual explanation in just in purely technical terms, because sometimes understanding the physical meaning of equations is not easy. Okay, so let me be here and let me do this. Okay. I hope that I can get it that easily. Okay. No, it's okay, but I think it is better than before. So, sea level and land. Okay, so the land, let me use a different color. This is the land, and this is the sea level. Into the land we have the groundwater level, the water table. Typically you have a level of groundwater into the land that is like this, decreasing toward the sea. Why it is decreasing toward the sea? Because if you want to make sure that there is a flow of water from groundwater to the sea, in order to have a flow, which is the situation that usually happens. We have infiltration into the land, we have rivers maybe feeding the aquifer, and therefore, what is the final receptor? What is the final destination of this water infiltrated? It's the sea. So typically you have a flow of water from the sea. This is what happens. And of course, if you modify the situation because there is a human impact or whatever, it may be that the flow is reverted and then we have saltwater intrusion. But in the understood situation, where we typically don't have saltwater intrusion, we have a situation like this. Of course, this happens if you have a permeable soil. Okay. In this situation, you have the flow of water from the sea, and that's it. Okay. So what happens to the seawater? The seawater infiltrates here through the seabed. And of course this infiltration, it's reduced if you have a flow of water from the land to the sea. But if you decrease, as we anticipated, the groundwater level, this may happen. If it happens, how does it happen? Also, it happens because seawater is heavier. Okay, so in this point here, the level of groundwater and sea is the same by definition, because we have groundwater that flows into the sea, so the level is the same. But here we have the seawater that is heavier, so we have some saltwater intrusion. And this saltwater intrusion happens like if you wanna, it's high, it's quite significant. As you get into the land, the groundwater level increases, and therefore the saltwater intrusion is reduced. And so you have a situation like this, where in correspondence of this separation between groundwater and seawater gets deeper and deeper as you get into the land, deeper and deeper. And this is why you have infiltration in this form of a wedge. Now let's, I understand that you may still have some doubts on the fact that why the separation is so deep. Keep in mind that it increases the depth of the separation. The explanation is that as you get inland, you get a higher pressure of fresh water which pushes the salt water deep in the ground. Keep in mind that if you didn't have any flow of groundwater here, you would have infiltration of salt water forever. You would have the salt water getting into the land indefinitely. And the only way it could stop is through a counter flow of fresh water or through a barrier like a rocky layer. And therefore, if you have a counter flow of fresh water, what does this mean? It means that as you get inland, the salt water is pushed down, 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 and down. And therefore, you have this kind of shape. Now, let's look at the mathematical explanation, which I think helps you in completing your understanding. Let me see. Okay. Let me see if I can get. Let me see the next one. think I need the blackboard for now. Okay, so we are talking of water flowing into the ground, salt water or fresh water. Flow is regulated by the Darcy's law. We mentioned it already. And what is the expression of the Darcy's law? And it says that the flow of water in the aquifer can be expressed as the product of a constant which is called hydraulic conductivity. I'm not sure whether you can read here, probably not. So let me focus here. This is the amount of flow in the aquifer. It can be expressed as a constant which is called hydraulic conductivity. It's a property of the soil and has the dimension, the unit of a velocity. And then there is the transversal area of the aquifer. Transversal means perpendicular to the direction of the flow. So the area of the aquifer measured perpendicularly to the direction of the flow. And then the gradient of the hydraulic head. So gradient of energy. And if we indicate energy with the symbol H, and we already said that this energy is measured as a length, because it's energy per unit weight, then the derivative of energy with respect to space, to travel, gives the gradient of the energy in space. So the flow is equal to the product of the area of the aquifer times the gradient of the energy times a constant. The gradient of the energy is adimensional because energy is a length divided by length is adimensional. K, hydraulic conductivity, has the dimension of velocity, and A is a dimension of length square. So velocity times length square gives length cube divided by time, which is fine. This is the flow. And keep in mind that in aquifers we can assume that the energy, in the energy term, there is no kinetic component, it's only potential. Why is that? Because the flow is very slow. What is the implication? If I can neglect kinetic energy, and the energy of the flow is just given by the potential term, it means that I can say that the energy of the aquifer is represented by the level of the water table. Level of the water table. So J for an aquifer can be assumed to be the gradient of the water table level with respect to space. So what tells us the Darcy's law? Tells us what I already anticipated, that to have a flow from the land to the sea, we have to observe a water table decreasing in altitude from the land to the sea. This is what we have to understand, which is important and was also implied by her in her presentation. When the water table level is decreasing in one direction, it means that there is a flow in the aquifer in that direction. This is why Darcy's law is important for us. Okay? So, please keep it in mind. Darcy's law is a way for us to prove that we need a water table decreasing in the direction of the flow. Darcy's law tells us that if by overpumping we lower the level of the water table below the level of the sea, we have infiltration of water from the sea to the land. This is why Darcy's law for us is important. Of course, you may say, yeah, but it's intuitive. Yeah, it's intuitive, but we are engineers, and therefore we need to understand this. Just for your information, here it's reported yeah, this is what I summarized. Let me see. I think I had in the web page. I have for your information. It's not reported here because it's not really important. I think I have here for your information. Yeah, this is a picture that describes the Darcy's experiment. Darcy's law was derived by Darcy through experiments, and basically what he did, he forced flow through a matrix of soil, which is named here with A, and A is, by the way, the area of the aquifer, because the direction of the flow is from the upper part to the lower part of this tank. So if we measure the area of the tank, it's the transversal area of the flow, and what he did was to force the flow through this tank and to this matrix of soil by making sure that there was a water level in the upper part that was higher than the water level in the lower part. In the lower part you have this water level, and in the upper part the water level is given by the other pietometer that is located here. And then he measured the flow, and for various differences of water level, and he could understand that the flow was related to the gradient of the energy. And he knew the length of the matrix of soil. This is basically the experiment that he did. Okay, let's go back to our presentation. Okay. Now, this basically says that the hydraulic end is given by the potential energy, with some more details because also it takes into account the pressure, but let's focus on the water table where the pressure is 0, and therefore we already discussed this. It's no problem. Now, let's talk about understanding of what happens here and why we have this, shape, wedge shape. Okay. Now, in order to understand the reason, we need to understand the hydrostatic law, which is very simple. But let me summarize it to you. Okay, let's suppose that we have water in static conditions. Like into a tank. And let's concentrate on a fluid particle that is not located at the surface, so not located at the water table like in an aquifer, in order to put us in a general context, a general situation. Okay, and let's indicate with Z the depth of the water column above this particle. And let's indicate with lowercase h, the height, sorry, I write better, of the particle with respect to a reference level, which for convenience I take at the level of the bottom of the tank. And let me indicate with capital H the total water depth into the tank. So, this particle is subjected to a pressure. The pressure is given by the water column above the particle. It is an excess of pressure with respect to the atmospheric pressure. How can we compute it? We know that the pressure over a body that is located at a depth Z of water, it's equal to the specific weight of water. Let's call it, I don't remember if I call it here, gamma F. Yeah, gamma F. Gamma F times Z. This is the pressure. The hydrostatic law, which applies in static conditions, says that if we compute the sum of Z plus P over gamma, this is constant. This is the hydrostatic law. Sorry, H. Sorry. This is the hydrostatic law. What is the implication of the hydrostatic law? The implication is that if I consider another particle with a different position, different H, and different pressure, anyway, the sum of position, energy related to position, plus energy related to pressure is constant. Which is understandable because we are talking about water that is not moving. So the energy of all these particles should be the same. Okay, and what is the value of the constant? The value of the constant is, we can substitute for the pressure, this expression here. And let me, here I forgot an F. So, if I write H plus gamma F times Z divided by gamma F, this is equal to H plus Z, which is equal to capital H. So the constant is the total energy of these particles. The hydrostatic law may also be applied to fluids that are slowly moving. So an assumption that we usually make when dealing with aquifers is that the hydrostatic laws applies also to the body of particles into an aquifer. Of course, you understand that this assumption is a little bit weak, not completely true, because in an aquifer, also if we have saltwater intrusion, it means that there is water flowing. So it's an assumption that is not completely true, but on the other hand, we understand that this flow is very slow, and therefore we can consider it a reasonable assumption, which is not valid if the flow is very fast. One other thing that I wanted to tell you, which is important to understand the mechanism of saltwater intrusion. If you look at this particle here, it is subjected to a pressure that is given by this relationship. The pressure, given that the particle is not moving, it's stopped, it's fixed, it means that the pressure is the same above, below, on the sides. There is into a fluid. The pressure that is exerted on a body is the same if on all the sides of the body. Okay, good. Now, let's think about a particle of fluid that is located on the separation into the land of salt water and fresh water. And let's assume that we have no flow. So let's assume that the situation is static, which again, you understand that it's not completely true, but let's suppose that it's static, because if there is a flow, it's very slow. Okay, so this particle that stays here, and let me redraw the figure here. The figure that I did before. And let me use for salt water this color. I hope that you can see the difference. And for fresh water, the blue. And let's draw an hypothetic, now a trial line of separation. This is an attempt, okay? And let's suppose that here I have a rocky layer. Just for convenience, because otherwise I should continue the drawing. And let's now introduce another important assumption. Let's assume that we have no mixing here. The surface of separation is a surface with no thickness, and therefore here it's a line. Again, you understand that this is not completely true. We have some mixing, but let's suppose that we don't have mixing. And let's focus now on a particle of water that is located on this surface of separation in static conditions. It means that the pressure on this particle of water is the same in all the sides, but I have two ways of computing this pressure. I can compute the pressure by indicated with h half the depth of water here, okay? But I can also compute the pressure of salt water. And the pressure of salt water is given by the depth of salt water, HS, here. Okay, you may say, yeah, but in this case, the pressure of fresh water is a real pressure because I have no soil. I have a real water column up there. So you may say, and that the pressure is different because my statement was not correct. You may say the pressure of fresh water it's more direct because I have less soil. The water column of fresh water that is present here goes through a reduced length of soil with respect to salt water, because salt water I move inland here in computing the pressure, but still if you think at static conditions, in static conditions it doesn't matter. So the pressure exerted by the salt water and fresh water over this particle is just given by the height of water above it, either salt or fresh. And then you may say, yeah, but then this particle is not in equilibrium because the height of fresh water is higher than the height of salt water. And my reply is no, because salt water is heavier. So this is why you need to keep this particle in equilibrium. You need a higher elevation of fresh water with respect to an elevation of salt water. So what happens if for some reason you decrease